All right. Welcome, everyone, to our webinar today as part of the AI for Hybrid Electronics webinar series offered by NextFlex. Today, we'll be hearing a presentation titled AI Opportunities in Electronics Manufacturing and Reliability. So just as a reminder for anyone who has not participated in any of our previous webinars in this series, NextFlex is looking at key opportunities in AI for hybrid electronics in ways to boost design and manufacturing efficiency, improve product reliability and yield, enable smarter and adaptive devices, level the playing field for small manufacturers, knowing that for small manufacturers, it's really hard to compete with large companies in some cases, and to strengthen the U.S. industrial-based resilience, which is a key element of NextFlex's mission. We've identified over the course of the last 7 months or so, as we've really been engaging with the NextFlex membership and the broader research and manufacturing communities in the U.S., many opportunities in these spaces, and we're excited to bring some of those ideas forward as we're also working to develop a roadmap for our future in this space. As part of that roadmap, we're really looking at ways we can accelerate innovation through AI and ML in things like design, manufacturing, and reliability, so across the gamut. There are really opportunities where we can align the hybrid electronics ecosystem toward a shared set of priorities using these roadmaps, help the broad community have a shared vision for where we can go and help them to get there together. Guiding and strengthening our investments at NextFlex in support of DoD transitions is another important element of this roadmap. Finally, we want to identify actionable and high impact opportunities across the value chain and support the workforce development for AI-enabled tools. The structure of this roadmap is really still coming together, but you can see many of the ideas that we have below for how the roadmap will be structured. The idea is laying out what's the state of the art today, where are we headed for the future, what are the opportunities, how do we pull all of that together with all of the key enablers as well as the key outcomes. So as part of that, we fit that all into NextFlex's broader mission. NextFlex, for those non-members in the audience, NextFlex is a manufacturing innovation institute partially funded by the U.S. Department of Defense, whose mission is to create a strong U.S. industrial base for hybrid electronics manufacturing. And we do this through 3 pillars. The first is advancing technology and manufacturing. The second is establishing and growing manufacturing ecosystems. And the third is securing human capital. That's our education and workforce development mission. To carry out this mission, we do a number of different activities. We operate our consortium with more than 200 members and partners from industry, academia, and government. We have technical working groups, 11 of them, that span manufacturing technologies and application spaces, technology platform demonstrators, we call them, in hybrid electronics, in which we develop roadmaps in each of those areas to build out the hybrid electronics future. We fund projects based on those roadmaps, identifying the top priorities for advancing the future. We invest in creating that future through our membership. We disseminate information, trying to level the playing field with knowledge through workshops and webinars like this one, as well as in-person events. Our member portal provides access to our members to technical project information, as well as other ecosystem information across the field. Our education and workforce development team has impacted more than 27,000 participants, including K-12 STEM education, all the way to incumbent workers in the field and in many states across the country. And finally, we have our technology hub. When NextFlex was stood up more than 10 years ago, the idea was to be not just a coordinator of this industrial base, but also a participant. So our technology hub is our manufacturing R&D prototyping facility in San Jose, California, where we can do anything from, say, material evaluation to first-of-a-kind prototyping to low-rate initial production, maybe in the quantities of tens of thousands of devices. So, right. Before we get started in today's webinar, I do want to highlight a few upcoming events. For NextFlex members, there's an exclusive opportunity, as always, to view project webinars. These are updates quarterly from each of the projects that we're funding. So over the month of December, we have 5 webinars that are scheduled. You can see the titles and the presenters for those. The January webinars will be announced soon. They have been scheduled, and those webinar announcements are just about to go out. If you're a NextFlex member, a tier 1, 2, or 3 member, and you want to receive the invitations to these project update webinars, please just contact Eliana Schoenberg. Her address is on the screen. Our technical working group road mapping activities continue. During the month of December, we're doing some in-house work and working one-on-one with individual members having completed the first round of technical working group meetings for this year's road mapping activity in November. The next round of TWG meetings will begin in January. Those invitations have been sent out. If you're an NextFlex member and you are not receiving those and you want to join any particular technical working group, just kind of send an email to Nick Morris and he'll add you to those lists. An opportunity for everyone. NextFlex Innovation Days will be in June this year in Mountain View, California, co-located with the TechBlick Future of Electronics Reshaped Conference. This will be a great opportunity to engage across the spectrum with NextFlex members and non-members through the conference. We're working closely with TechBlick to ensure alignment. We're providing speaker suggestions to the conference, and we'll be having some NextFlex member-only activities in coordination with that. So the registration for the NextFlex portion of that event will go out in January, and the conference registration is already open. Finally, last save the date, we have the next in this series, this webinar series, the AI for Hybrid Electronics webinar series will be presented next Wednesday, December 10th. Same time slot as today's webinar. This will be harnessing the power of AI and FHE design, understanding challenges and unlocking opportunities. And our presenter will be David Wiens from Siemens. So taking an EDA view on this AI opportunity. All right. It's my pleasure now to introduce today's speaker, Professor Pradeep Lal, the director of the Electronic Packaging Research Institute at Auburn University. I won't read Pradeep's bio to you. He is a distinguished professor in mechanical and electrical engineering, has authored numerous books and articles. Pradeep is also the principal investigator on several NextFlex funded projects over the last 10 years, including some that are active today, and has done a lot of work in the area of AI even well before the current AI boom began. And so we're very much looking forward to Pradeep's views and presentation today. Pradeep, I'll hand over to you. All right, we see your slides and your video. It's all yours. Oh, but you seem to be muted.
Can you hear me?
Yes, we do.
Okay, perfect. Thank you for that introduction, Scott. I think what I'll do today is I'll talk a little bit about the opportunities in electronics manufacturing and reliability as they pertain to artificial intelligence. And what I hope to convey as a part of the webinar are some of the methods that are presently tractable to apply to this particular field. And I'll give you some examples of how these methods actually have been applied in some of our own work over the last 20 years. So I had a slide about the instructor, but since Scott has already introduced me, I'm going to go ahead and skip this. So the primary motivation for looking at reliability in defense systems in a lot of the harsh environment electronics applications is the fact that much of the equipment actually is used beyond the initial design use life of the equipment itself. So one example, for example, is the B-52. So this is from the USA Today in 2002, and it states that B-52 first lifted off in 1952 and is intended to be flying till 2040. And so one of the things that happens in these long life systems is that one needs to assess life mission preparedness continuously. And this is one area in which AI methods and AI systems can actually make a huge contribution to the state of art. Now, what is the technology gap? The technology gap is we really need to be able to develop correlations between accelerated test performance and the field life. We also want to be able to understand the accrued damage in some of the field returns, for example, that have come in. Many of them, for example, may not have any major indicators or macro indicators that are discernible. And so prognostics is a major area in which AI systems can actually truly make an impact. So this is the view of how AI can contribute in contrast with what is traditionally done today. So what is the traditional view of reliability? Traditional view of reliability is this left box, where we want to do life prediction. Life prediction models, for example, may assume a pristine material state. They may have a known stress strain, temperature, relative humidity history. And then we assume that under that relative humidity history, we try and build a model with a known constitutive material behavior. And then we predict how long that system is going to last. Prognostics, on the other hand, doesn't do any of that. It basically says, I want to be able to use methods where I have a field deployed system and I have a material assembly with an unknown degradation state, and I have unknown stress strain, temperature, relative humidity history. And I want to be able to determine the state of accrued damage and the remaining useful life. And that is the problem that we want to be able to address with artificial intelligence. Now, broadly speaking, we know how to diagnose failure. So in present day test methods, we can diagnose failure using a number of different ways, using event detection, using data acquisition systems, using measurements of resistance or other indicators that may indicate out of bounds drift of the system itself. But broadly speaking, the challenge in electronic systems, especially complex electronic systems operating in harsh environments, is slightly different in the sense that we actually can't have the system fail in operation. So for example, this red circle here indicates the present time in operation. We are tracking some feature vector, which I'll explain what that means a little bit later, over time, and the feature vector is changing as the system is in operation. And there is a point in the future at which the system is expected to fail, but that time is not now. And what we want to be able to do is we want to be able to determine how much time there is before that impending failure is materialized, and more importantly, how much time do we have to be able to undertake any meaningful intervention, such as to do repair replacement of the system to prevent catastrophic failure. So we might begin by, for example, establishing a failure threshold. We might begin by establishing a detection threshold of this feature vector before the feature vector actually gets to a location where we are able to determine that a failure is imminent. Now, in order to do that traditionally, what we would have to do is test a whole lot of parts and create a failure distribution and have a probability density function of this failure data so that we can determine under a range of conditions when failure is going to occur. The bigger problem in being able to do this is the fact that this is very time consuming, number one. Secondly, it's very expensive, and it would require us to test a very large number of possible combinations that may be experienced in operation to be able to build this failure distribution. And theoretically, if we had one, we would basically then identify a location in that distribution which allows us to determine what is the maximum allowable threshold for failure. So depending on the criticality, typically this might be B10 life, that basically means 10% of the population has failed, or B1 life, 1% of the population has failed, and really depends on criticality of the system itself. So this is kind of the lay of the land when it comes to reliability and what it is that we are trying to surmount with the use of artificial intelligence. By the way, just as a side note, many of these graphics are sourced from our prior publications, and the publication actually is listed at the bottom of the slides for folks who want to go back and study more than what I'd be able to cover as a part of the webinar. So in terms of remaining useful life, how do I determine what is the time at which meaningful intervention might take place, right? So one way I would do that is I may have early system state sensor cells. I might interrogate the system state using measurements from these sensor cells, and then I might identify the remaining useful life from these measurements using computational algorithm, and using those measurements, I can determine the spot assessment of how the system is actually doing presently. And depending on what the remaining useful life might be, I might put certain confidence bounds. So 1.96 really translates to 95% confidence bounds. And then the lead time in obtaining replacement parts to be able to identify when the intervention is going to actually occur. So an engineering implementation of a prognostic health management system that uses artificial intelligence might look something like this, which basically says, I have a complex electronic system and I can't have that system fail. So I'm going to use a set of sensors that provide me data, and I'm going to use that data to create features. I'm going to use those features to classify what failure modes exist in my population, and I'm going to track those features to be able to identify the current damage state and the future anticipated damage state of the system. And using that anticipated damage state, I'm going to determine the remaining useful life and the uncertainty in the prognostic distance, or the time before failure of the system itself. So now artificial intelligence is a fairly large field. There are various categories, and so what I'm going to do is I'm going to go through at least some of the taxonomy as it pertains to AI before I start to use it as a part of the opportunities and that may exist within electronics reliability and manufacturing. So AI is kind of a super field that involves methods that allow one to emulate human behavior. And the human behavior that we are trying to emulate are things like decision making. We want to be able to perhaps recognize failure patterns, failure mechanisms, failure modes. We want to be able to solve very complex problems. Within artificial intelligence is a subfield of machine learning. So ML is a subset of AI that is often used to detect patterns in these large data sets. It allows machines to develop and adapt, and we might use both supervised and unsupervised learning methods. So I'll cover those a little bit later on in the presentation. So I'm going to put those on the side, but recognize the fact that there are two types of methods, supervised and unsupervised. A subset of machine learning is deep learning, and deep learning really leverages ANN stands for artificial neural networks. Effectively, deep learning methods use intermediate layers of these neurons to be able to extract high-level features from raw data. So raw data might be high-dimensional data, and we want to be able to extract features that are meaningful to change in the system state of the electronic system. A subset of deep learning methods is generative AI, and these are there are several examples of these. So ChatGPT, for example, is an example of a generative AI methods, and typically what these methods do is create content. They are able to generate content. They have pre-trained models, and they can create human-like content, text, images, video, and they may also be trained on a mix of supervised and unsupervised learning methods. So I'm going to contrast machine learning versus generative AI next. So typically machine learning, we really are working with data, for example, that may be structured. So what does that mean? That basically says I have data, and then on that data I have labels. So in the case of electronics reliability or manufacturing, it might be a defective part that I've produced. What does the population look like versus what does the population look like in undefective parts? What does the population look like in parts that have impending failure versus a population that is pristine and does not have a failure mode that is currently active? And we might build a predictive model that learns the relationship between the data and the label, and then the output might be a label which the algorithm identifies based on the fed data to be able to say, oh, that particular data set looks like the electronic system is going to fail, or that part that has been created as a part of the assembly line output is a defective part. Unstructured output, on the other hand, really takes content that is not labeled in this well-defined manner, and this unstructured input can then be parsed using tokenization and a bunch of other methods, which is what is used to train generative AI models, which learn the pattern in this unstructured data and then are able to provide human-like content, new content, text, images, video, based on queries that the user might pose to the system itself. Supervised data. So this is labeled data versus unlabeled data. So unlabeled data, as I mentioned, might have a name. In each data set, you are pairing that specific data with the specific label. And the objective really is to learn the mapping from the input features to the output labels. That's really the idea of the labeled data set. And the supervision really implies that it requires human intervention to provide the correct labels during the training phase. So that's really what supervision entails. Unlabeled data, it basically only contains input features that are provided without any corresponding labels. You don't say how many failure modes might be existing in the data set, or if there are any defects in the input data. And the objective really is to identify the underlying hidden patterns and structures and relationships. And there is no supervision that's required. And I'll show you examples of both of these as a part of the webinar as well. The generative foundation models, so there are typically 3 flavors that are commercially available today. So there are several text-based foundation models. So as I mentioned, generative pre-trained transformers, or GPT, Chat GPT, for example, BERT, Llama, which is the meta version of the foundation model. These are text-based foundation models. There are several image and multimodal foundation models as well. Examples: DALL-E, Stable Diffusion, Clip, and there are several audio-based models as well. Whisper, Music, LM are examples. So these are pre-trained models that can be readily used by a user to be able to either submit queries to, or extract data, or generate new content from. So this table really compares generative AI with machine learning examples in the context of a number of different tasks. So image generation is something I mentioned a little while ago. A generative example would be to be able to create new art. A machine learning example would be, for example, to classify an image or detect an object. And there are similar analogies from music, art, gaming, video, voice, and text as well. Okay, so if one looks at applications with relevance to AI and ML in the field of electronics, so these are some examples that come from a paper, a fairly recent paper, and you can look at what the opportunities are in terms of applying artificial intelligence and machine learning methods to the field of electronics manufacturing, be it in fabrication, assembly, semiconductors, or hardware, and what are the kind of things that we are trying to do, things like quality control, things like manufacturing consistency, repeatability as a part of the manufacturing output itself. So I'll give you some examples, and then we'll delve into more in-depth methods that can be used for electronics reliability and manufacturing. So let's say we are in a high volume environment and that we are trying to output a fairly large volume of electronic product on a day-to-day basis. We install a machine, the machine is inserted into its first use, we acquire some data on the state of the machine is then put into operation, we continue to acquire data on the state of the machine. And then once the machine is in production, is used for the purpose of manufacturing for high volume product, you start to acquire what's called the health of the machine itself, or the asset. You're monitoring the asset and trying to determine if the machine is in its normal state, is it in its faulty state, is there an impending failure, is there expected downtime that would require, for example, intervention for replacement of the part such that there is no downtime on the line itself. You may also, for example, look at the machine output to be able to classify defects. You might be able to look at the machine or the part that is being manufactured to be able to determine what the expected use life of the part might be based on a stress screen that is run as a part of the production process itself. Now, why is this so critical for current and future electronics? So the primary reason why this becomes very important is because electronics complexity is increasing dramatically. So it is widely expected that packaging complexity is going to increase. The next generation architectures are often referred to as heterogeneously integrated packaging is very complex. When you're trying to assemble devices of this level of complexity, the impact of failures even during the assembly process can be immense. And therefore, further down the line, failures are much more harmful than if a defect is detected much earlier on in the process. So AI-based methods can be impactful from that standpoint as well. And more importantly, there are limitations of the physics-based models that we use today. We actually are not able to keep up with the complexity of the architectures, number one, and also be able to characterize the damage relationships and the constitutive behavior at a fast enough pace to be able to make an impact. So I'm going to drill down into the actual AI-based methods, and I'm going to start off with a case study. So imagine that we have a scenario in which an electronic system has been in storage after manufacture. So this happens a lot in defense systems where things actually don't go into a mission or are not deployed right after manufacture. And then a system, for example, is extracted from storage, transported to a place of use. However, during transport, it's subjected to road shock. It now needs to be deployed in a mission critical application, and we need to determine if the system is identical to the pristine state and is capable of completing the designated mission in the operational environment. So it's a very real scenario. It's something that happens in a number of different fields that have long life systems. Automotive is another example from the consumer products that has a similar profile as well. So if we were to use AI, so this is the analogy between the human brain neuron and an artificial neuron. A human brain neuron, for example, this is the cell body of a nerve cell and may have dendrites. It has an axon, and then it takes the signals from the dendrites through the axon to the synaptic junctions or the synapses. An artificial neuron takes inputs, and the inputs are analogy to the dendrites. There may be multiple inputs. There may be 2 inputs, 3 inputs. They might more complex models may have thousands of inputs. These inputs go into a perceptron, which is a digital view of the human brain neuron. And this perceptron then reacts to the inputs based on synaptic weights and provides a net output. The net output value, depending on the value, whether it's negative, positive, may go to an activation function that may provide, for example, an output. So positive values may provide. So this is a step activation function. Positive values provide a step positive output. Negative values provide 0. But there are a number of activation functions. This is just one example. Piecewise linear activation functions. They are sigmoidal. They are tangent hyperbolic. There are a number of activation functions that are used in the field of AI. And then at the end of the day, you get an output. And that output would be what it is that you're looking for. As a part of the training process, you want to make sure that the output is what you expect it to be. And once the AI model has been trained, you want to be able to use this on previously unseen data to be able to identify the task at hand, be it the remaining useful life, the occurrence of a specific failure mode, the propensity for failure, or a deviation of a machine from normal operation. So I'm going to give you an example. So this is from the area of mechanical shock and goes back to the example that I was providing here. And what we are doing is we are taking a system. So this is how it has been put together experimentally. And if you want to learn more about this, you can read our paper. But effectively, you would take this system and you say, okay, I'm going to look at how shocks, for example, impact the system. The system may not fail in the first shock, but I'm going to acquire data. And from the data, I'm going to extract features. And from those features, I want to be able to classify them to determine uh, what feature corresponds to what specific failure mode. And using that feature classification, I want to be able to cluster similar looking failure modes in similar parts of what's called the feature space. Okay, so now, for example, what does a feature mean? A feature basically means a data vector, a set of numbers that corresponds to a specific failure mode. So that typical feature is machine understandable, but may not make sense to a regular person if one looks at a set of numbers to say, aha, that set of numbers correspond to that particular failure mode. But a machine learning network or an AI method can actually do that. So as an example, you may have an input layer, and the input layer might take various inputs from the system. You take those inputs, you might feed them to a hidden layer. The hidden layer may go to other hidden layers, and the final layer might provide, for example, an output that provides you a categorization of the failure mode. So this is a system in which there are multiple failure modes. For example, there might be a system state that's healthy. There might be a system failure mode which includes missing solder joints. There might be failure mechanism that has cracked solder joints, chip cracking, chip delamination, or a part fall off. So these are various examples of possible failure modes that may exist in a board assembly. So the way you would approach this is to take that input data. So I showed you this input data. That's higher dimensional data, too many numbers to be able to actually graph in a geometric two-dimensional or three-dimensional feature space. You want to extract features that are meaningful. And so one way to do that is to do dimensionality reduction. There are a number of methods that exist in the state of art to be able to do that. We have used one of these dimensionality reduction methods to be able to identify two dimensions. So for the purpose of graphing, they have been labeled as dimension 1 and dimension 2. And the idea is to be able to plot the various failure modes in this particular feature space. So you notice healthy is this star, and this square, blue square, is solder cracking. That's SC up there. And what I want to be able to do is I want to be able to train my neural net such that it can separate out these parts of feature space to correspond to different failure modes. So we start off with a randomly initialized perceptron, and you see the slope of this perceptron is changing. It might oscillate as the model trains. And finally, it's going to say, okay, I'm going to reside as this red line where on one side, I only have solder missing, and on the other side, I have everything else. And what you want to be able to do is take this labeled data and be able to separate out the feature space in this manner to say, okay, that's where solder missing resides. That's where chip cracking resides. That's where part fall off is. That's where solder cracking is. And that's where healthy is. And you separate out and segment the feature space. And so now if you have a functioning system, one can now determine what the state of the system might be. Now, this is an example with label data. Now, what if I don't know? I don't have data labels. What if I don't know how many failure modes are active in my particular system? What do I do then? So this is a different example. This uses a method called self-organized mapping. Again, a separate paper on this particular topic. And that has been applied to an electronic system, again, in mechanical shock and vibration. So SOM, or self-organized mapping, undertakes a three-step process of competition, cooperation, and synaptic adaptation. In the competition process, under an input that's provided to this 2D or 3D topology of neurons or neural nets, the neurons compete amongst themselves, and the one with the highest output, the highest amount of activation, is the winning neuron. So here that's indicated as a black dot. And you might have a neighborhood that may be activated as well, but perhaps not, doesn't have as high an output. And then there are a whole bunch of other neurons that are not activated. And then over time, these neurons that are in the neighborhood cooperate to shrink the neighborhood such that similar uh, patterns in the input data always occur in that neighborhood of the neurons, neural net or neighborhood of neurons. And then you might undertake synaptic adaptation to be able to separate out the boundaries from other patterns that may exist in your data set. So I'll show you this example. This is an actual heat map of an assembly. So this is, again, experimental data. Again, you can look at the paper of shock events versus frequency bins. And so the one thing that you'll come away with is the heat map indicates that so this is spectral content. We are plotting the frequency moment. So this is in a shock event, which is a transient event. An electronic assembly actually undergoes shock, and the spectral content evolves as a function of time. So the frequency moment is the specific time delay of a particular frequency bin in that time signal. And so that basically shows you on that scale that the spectral content is continuously changing as the assembly accrues damage. So that's one thing you can come away with. And then what you do is you do this dimensionality reduction. That's kind of what we have done here, and change the matrix. And that second step I was telling you about, cooperation. This is the neighborhood shrinkage. So typically when you train an AI-based algorithm, it goes through what is called epochs. These are training cycles. So epoch 1, 10, 100, 1,000, 10,000. Again, so this kind of shows you how the neighborhood shrinks. So you might have a bell-shaped curve like this. That shows the topology of the activated neurons of the self-organized map. But after 10,000 iterations, the neighborhood might look much, much smaller, which is what you would want to have happen. So generally in a neural net, data that's much more recent is considered much more relevant than one that's that occurs much earlier. So you have what is called a forgetting term. A forgetting term, so I'll identify certain products. So that's my learning parameter. That's my topological neighborhood. And W is my synaptic weight. So initially, we initialize the synaptic weights randomly. So you can actually see in this three-dimensional space, dimension 1, 2, and 3, you can see they are all over that particular dimension space. But as we go through training from 1 to 100, it takes a certain form, go to 1,000, that form changes. And 10,000, it looks quite a bit different once the network is completely trained. And these are what the weight vectors might look like. So since they're randomly initialized, that's what the weight vector looks like in that three-dimensional space. And after 100 training cycles, it might look something like this. After 1,000, it might look different. And after 10,000, it might look something like this. So the process of training actually allows the network to modify itself. Now, this is a unified distance matrix. If you look at the different epochs, you'll see actually the patterns are changing. This is what happens when I have a data set in which there are multiple failure modes, but I don't tell my AI system what those failure modes are or how many there are. And I want the system to identify, self-assess, and identify those failure modes and assign pockets of similarity, so to speak, so that we can assign labels. And so the light pockets are pockets of similarity. The dark boundaries are dissimilarity. They separate out individual areas from each other. So this is what this would look like once it has fully run. Each of these areas that I was showing you, for example, if I didn't identify the labels, that's solder cracking, that's solder missing, that's part fall off. And each of these labels, that's chip cracking, corresponds to a different area. And this is what the topological map would look like. So you can identify the different failure modes that may exist in the data set itself. And that's what the output would look like in a self-organized map. So that's actually experimental data that we did as a part of a shock test. And this was then used for unsupervised learning. So this self-organized mapping is an example of unsupervised learning. I'll show you a couple of other examples. This is for a feature vector, for example. Feature vector, as I said, consists of different numbers. This is, again, a different paper, a more recent paper from 2023. Number of different parameters, RMS of residual of cross correlation function, mean of residual variance kurtosis, and then the remaining useful life. And ideally, what you'd like to have happen is you want this feature vector to change right before failure. So these are before failure points, those are after failure points, and you want the feature vector such that it provides a leading indication of failure. That is, a failure is impending but hasn't occurred yet. So this is a different method. It's called long short-term memory. That's what's been used in this particular case. And the idea is that you can control the amount of long-term memory that's forgotten. So traditional neural nets, you basically weight the shorter term data, the more recent data, and try to forget the long-term data. The LSTM methods allow you to control the amount of long-term memory that's retained through control of a gate, this gate, which is called a forget gate. And so you can pair the short-term spot assessment of the system with what we know long-term about the system. And that allows for a much more stable output while allowing plasticity for change in the system state itself. Again, this is a three-dimensional space. Red are the before failure points, blue are the after failure points. We like to be able to separate these out. This is what's called an alpha lambda plot, and it is often used to assess the accuracy of the algorithms. And ideally, I would want to be in this green cone of the remaining useful life, and the red line is the prediction of the system. So ideally, I want to be able to track where I'm at in the context of the system state itself. So I'll show you an example of how this might be applied experimentally, and this has been implemented again in this particular paper. For those of you who are interested, can refer to that. But typically, what is measurable is strain in assemblies. We can't actually measure plastic state in individual joints. So what this method does is really tracks the board strain to be able, from the back of a PCB, to extract features that are strain-based and do feature state identification and use the feature state to assess the current damage state of the system and assess remaining useful life. So I'll show you an example. So typically, something like this, in shock or vibration, is done using FEM. FEM stands for finite element method or finite element analysis, FEA. And that's the blue curve. The LSTM prediction is the red curve. This is plastic work versus time in seconds per shock or vibration cycle. It kind of shows you how they track with respect to each other. A finite element model would take several days to make, would take a couple of days to run after the model's been made. The LSTM model, once it's trained, runs in real time. And you can actually see how the red curve, which is basically the actual RUL, how it tracks relative to this green cone in the two cases. So one can actually do real-time assessment of system damage in these highly transient environments using AI-based methods. So this is what it would actually look like, right? So because we are doing prognostics health management, which is what I started off this webinar with, we may not have all of the data available, right? The entire future of the part may not be available. So this is a board assembly that's running on a shaker system, and we are monitoring resistance using a method called resistance spectroscopy. If you want to learn more about that, again, you can read some of the papers in the footnote. And we are using a method called Kalman filtering that allows us to model the system state and then predict what the future might look like. And because the amount of data that's available to the algorithm is very limited, it might say, oh, it's going to last 10 hours. But reality is, if we tested the system out under the same vibration, it'll actually fail in 5.5. But the algorithm doesn't know that. So time goes by, more data becomes available, or bounds shorten, and the system basically, AI system says, okay, I know better now. I don't think the system's going to last 10 hours. It might only last 7. And more time goes by, and now at 4 hours, it says, okay, well, it's going to fail right after 5.5. So the more data we have available, the better the system does in terms of remaining useful life prediction. So that's actual experimental data and an AI system actually running on it to be able to assess remaining useful life in real time on an electronic system, board assembly. So, so the last few slides, I have 3 or 4 slides. I'll give you an example from one of the prior NextFlex projects that Auburn led. This was on closed loop control, in which we developed a method to determine the printed line width based on system print parameters. So that is kind of difficult to do in many of the additive platforms. And the one that we implemented this on was the inkjet platform. There are a number of different parameters that are shown here. The parameter levels, we developed a data set as a part of the program. We actually developed a software interface and delivered this to NextFlex as well. But again, there's a paper on this. And the method that we used was deep learning method. So what we did was we acquired data in real time using an optical camera and a Raspberry Pi system. We'll take this optical image, we'll translate that to a grayscale image, we'll binarize the image, and then we'll do edge detection. So there were separate algorithms for that that were implemented. And then once we do that, we measure the line width. Line width is what we were looking for. And from that, we'd extract a whole bunch of other parameters using a separate set of methods that looked at assessing the printed resistance, capacitance, and inductance. I'll just give you an example in the interest of time of just line width. And what we did was we said our model is going to look something like this. This was based on what we thought the data was doing, and we used a method called neural network regression. So regression is a part of statistical methods. Instead of using statistical methods to regress data, we said we're going to use neural networks to create the regression model. And we are going to then allow the neural network to continuously take in new data and update itself based on the current state of the system so that it can still correctly predict line widths. And that was the model that we started off with. And then we actually do the estimated line width and the variance around it. We use 6 hidden layers, 1 input layer, 1 output layer. There were 100 neurons. And I mentioned activation functions earlier on. We use a sigmoidal activation in this particular case. This is what the output looks like. So basically, the neural network model is used to update the equation. This is one of the intermediate states, not the final set. This is what the equation would look like. You see the line width data that's been acquired, and as time goes by, we get more data, and then the root mean square error basically drops precipitously as the model gets to know its state better and better. So this is how one possibly can use AI-based methods for doing closed loop control in the context of additively printed flexible hybrid electronics. So this is what the closed loop system would look like. So first step would be inputting the initial parameters. Second step would be image processing. Third step would be checking the print quality. And fourth step would be deployment of the deep learning network to be able to update the parameters of the system. So we put this in a closed loop control type of a system where one can not just look at the line width, but also identify what parameter values need to be adjusted to be able to get to the target line width. So that's how closed loop control was enabled. So with that, I'd like to summarize. So couple of thoughts I want to leave with you as we end the webinar. The emergence of AI methods opens up a number of opportunities in manufacturing and reliability. Hopefully you came away with some of those opportunities in the state of art and how they may be used for electronics packaging, assembly, and test. I gave you a number of examples from anomaly detection, from fault mode classification, from feature identification of impending failure for rapid life assessment during operation and closed loop control. In each case, the results from experimental data were covered along with the resulting predictions. Thank you for your attention, and I'm happy to take any questions if there are any.
All right, Pradeep, thank you very much. Excellent presentation. You covered a lot of ground within it. So for the audience, we do have the questions pane as one method that you can use to enter your to ask questions. You can also raise your hand in the GoToWebinar, and we will be able to unmute you so you can ask the question yourself. But why don't I get things kicked off at first? So, Pradeep, you showed a lot of examples for how AI and ML techniques can be used for things like defect detection and lifetime prognostics. How do you suppose we would deploy those techniques, say, in the field? If you have parts that are, out integrated into a system, whether that's an automobile or an airplane or some other system, is there opportunity to take some of that data in real time and feedback so that we can act on what I guess would become AI prognostics for health before we experience catastrophic failure? Or are you going some different place with this?
No, I think I think you hit the nail on the head. I think that's exactly right. The intent is actually to acquire field data from fielded parts. So traditionally, the way reliability has been addressed is by looking at material constitutive behavior, by looking at, for example, damage that may be accrued, and then identifying failure when it occurs. There are a number of fielded systems that actually do that. So on the aerospace platform, for example, that might be done as a part of the ongoing health management of the platform itself. On the automotive platform, there is a system called OBD, onboard diagnostics, that actually determines the normal operation of the system. And if the system, for example, deviates from normal operation, the onboard diagnostics would throw up what's called a diagnostic trouble code that shows up as a fault indicator light on the dashboard of the vehicle to be able to indicate that a system actually has failed. What we are trying to do with AI is actually step back from that catastrophic failure threshold. So we are trying to look at the system in the pre-failure space. So normally operating systems, like in the example that you gave on the aerospace platform, or other systems such as the automotive platform that are long life systems, have data that for example, can be that can be acquired to identify what the system is doing. Is that data, for example, providing features that are changing in state space that might identify that the system is migrating over a period of time from a state that it was at to a state that is closer to an impending failure. We can identify, for example, the change in state of the system. We can also identify, for example, if the system was to be inserted into a mission critical application, what the probability of the system completing its mission is, so that risk mitigation measures can be taken, and at least an informed decision can be taken whether or not the system is mission ready. So those are the kind of decisions that actually we have not had the ability to undertake. Typically, part replacement in the present day climate is done based on rules and guidelines and fear of failure rather than the spot assessment of the system itself. And that is something that AI can actually truly enable using many of these measurements.
Excellent. So we have a question from Suresh Sundaraj. Suresh, you should be able to unmute now and ask your question.
Yes, thank you very much. Professor Pradeep, excellent presentation, gives a clear view of your research work. The question I had was, when you are, how much confidence do you have in the AI model versus the finite element model of, let's say, a life prediction, let's say a Sherlock or something, which is predicting the solder life, for instance? Do you believe that the AI model can give better predictions to measurements as opposed to the finite element model? I know you're training it on the experimental data set, but you were also using some finite element method, right? So if you can just talk to that, that'll be wonderful.
Yeah, no, excellent. So I'm familiar with Sherlock. Sherlock is really based on closed form methods. It's now a part of the ANSYS tool set.
Mhm.
And I don't mean to knock find elements particularly. I actually teach find element methods course here at Auburn. So certainly
Yeah.
the field is very near and dear to my heart. Um,
Uh-huh.
but more directly to answer your question in terms of closed form model comparison with AI-based methods, closed form models generally are first order models. They really are based on uh, simplistic assumptions of the way the structure is going to behave under known environmental conditions. And they have hard coded, for example, damage relationships in them to assess what the predicted state of the system, be it strain range, be it plastic work range, be it stress range, uh, correspond to in terms of field life. And they're great for actually assessing what the system design inherently is capable of doing. Where the AI methods really help is in assessment of newer architectures, and also when there are um, operational environments for which you have no historical data or no existing models, right? So, for example, you transition to a new material. For a common example in the present day climate, historical models are based on tin lead solders. They might be based on
Yeah.
SAC solder, which contains 3% silver, 0.5% copper.
Yeah.
Newer generation of alloys, for example, focus on low temperature solder alloys for which I may not have constitutive behavior or damage relationships. Therefore, that basically excludes the possibility of one using a tool like Sherlock or a closed form model, and so that opportunity does not exist. But an AI-based method where I am trying to train the model based on existing data on a known assembly can be used to do prediction without me having access to the constitutive behavior or the damage relationships. A second advantage that I think AI-based methods have uh, is in terms of uh, the ramp up time, so to speak. Ramp up time for a newer geometry or a newer assembly. A find element based model might take a long time to create the geometry, to be able to run the model. I can do real time assessment using an AI based method. And so I think if one, in the end, I don't believe they compete directly. They actually uh, address very different needs in the state of art.
Thank you, Pradeep. So I have a couple of other questions for you.
Thank you very
We
much.
have time for one. To your to that final point that you made, one of the interests that we've heard and seen actually and done some work in ourselves is looking at deployment of edge AI solutions. So edge devices employing some kind of machine learning and AI. Do you think that there is either a cost or a benefit to deploying, or maybe a combination of the two, of deploying these techniques on, say, low power edge devices that either may or may not have real-time communication?
So I think one of the dirty secrets in AI-based models is they require lots of data, and they are very data hungry. And more data is always better than less data. And I think to the extent that edge-based devices provide us access ever close to the point of application and the point of usage, um, and they provide us more plentiful data at multiple locations than we would, for example, and that data can be provided in real time. uh, Edge devices have a massive advantage in asset monitoring of critical infrastructure. They can provide uh, instantaneous insight into the state of health of a critical infrastructure or a critical asset that's a part of the infrastructure by interrogating the state of the sensor output, constructing feature vectors, and seeing where those features reside in the feature space itself. I think the bigger uh, issue in many of the edge devices has been that these edge devices themselves require power sources, and 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 how long can those power sources stay active to be able to provide that data, and how much of that computation can be done at the edge as opposed to offloading the data offline. And that's, I think, where a huge technology gap resides. Can we decimate the data to a level at the edge and be able to extract features at the edge so that that computation is not really have to be done offline, but rather is done in real time on the system itself. And that's something that has yet to be surmounted. Most of the AI-based methods and algorithms really reside on very high power CPUs and GPUs, and they're not as amenable to these lower 8-bit processors that are often used on these edge devices. So I look forward to the day when we'll be able to do that.
So pretty, I know that we are at time, but we got a question that came in as you were answering that question. Very specific niche case, but something similar to the question that I had asked you. For gun-hardened apps, there are devices which are powered on after the launch, but the initial extreme G shock occurred when the device is powered off. How would these models work in such cases?
So I think the models would work very similarly. The models would work in a way such that the system response of a pristine system is known under low G shock that is not operation level shock. So operation level shock in a gun mounted system, for example, might be around 10,000 Gs, might even be 50 or 100,000 Gs. But the test shock levels that are used to develop the models are much, much lower. They are more like 5 Gs and 10 Gs and 20 Gs, something that might be encountered, for example, in transportation handling, mounting, or deployment of the system itself. And so once the model is trained, the model would actually run in the unforeseen scenario as well that would be able to monitor the state of the system at a much higher input level.
Can you imagine a situation in which we design, say, features that are meant, you want to interrogate that 10 or 20 or 50,000 G event, but you know that your device is going to be powered off until that event has occurred. Can you imagine designing in features that would provide data to the system once it has been powered to kind of back out what occurred previously? And would that be useful?
Yeah, so there are methods, and there are methods for reconstructing past state of stress histories based on current state of features and the state of feature evolution. There's a separate set of publications that we have worked on that extensively as well for thermomechanical applications more than for shock applications, and I'm happy to point you to those. But broadly speaking, we do test up to 100,000 Gs in my lab. We have setups that actually do 100,000 Gs of testing. We have videos that I can show you what those electronic systems look like at 40, 60, 80, 100,000 Gs. Once the shock pulses get that high, the frame rates to be able to acquire those events have to be significantly higher so that we can slow those events down and look at what the deformation history would be frame by frame. To the extent, I think one of the things you're alluding to in the question is, are there some parameters that can be measured operationally once the system powers on to be able to determine the state of health of the system and the past accrued damage and the remaining useful life once the system has powered on? So electrical parameter interrogation is something also that we have worked on immensely, and there is a rich body of literature on that. Depending on the system, there are a number of methods in the field that would allow you to create feature vector based on electrical measurements of the system itself, be it response time, the rise time, the fall time, the dwell time of a clock signal, for example. Those are examples of parameters. Resistance spectroscopy is something that I mentioned earlier on. Phase delay is another parameter that we have worked with extensively. And so there are parameters that can be used to extract features that would then be used to assess what the damage state of the system might be and reconstruct possible equivalent states of damage to be able to identify what % of the life has been consumed. So you cannot create the exact past history, but what the methods that we have developed allow you to determine what is the % of life that has been consumed. So that kind of gives you a sum total. It's what's often called in statistics as a Q sum, a cumulative sum of accrued damage till that point in time. And so that's how we have approached it. Yeah.
Great. Well, thank you very much, Pradeep. Excellent webinar. And for the audience, I hope you'll join us again next week when we hear David Wiens from Siemens talking about applications of AI tools in electronics design. All right. Thank you very much. Look forward to seeing you all next time.